Good morning. It's a pleasure to be here and to see so many people turning up for a Smalltalk conference. So the title of my talk is a little bit strange. I hope by the very last slide you will have understood the title. I'm going to begin by making an observation that there are a lot of programming languages out there. And Bill Kinnersley maintains a list of all those he has been able to find, and there are currently more than 2,500 programming languages. Underneath is part of a wall chart that shows just 50 of those languages and the evolution in time of those languages. Now, you can't see very much on the scale that I have here, except that there's a lot of cross-fertilization between programming languages at the beginning, back in the 1950s, 1960s, and a little bit of that occurred again in the early 1990s, but most of it has died out by the year 1990, which is something that a chart like that shows very well. Another chart that shows something interesting is a list, if you like, a picture of all of the books that O'Reilly publishes about programming languages. And there are very, very many books published by O'Reilly. All of them have funny animals on the front. But many of them are about languages that are pretty similar to each other with very little difference. And the resolution here is terrible. I apologize for that. But this is a chart that, instead of by chronology, shows programming languages by influence on each other. And so let's see if this will work. For example, up here we have Similar, and here we have Smalltalk, and we have Sketchpad. Similar, Sketchpad, both making Smalltalk, and then Smalltalk, of course, spawning several other languages, including, let's see, there may be Ruby down there somewhere, I'm not sure. Ruby was Lisp and Smalltalk, I think. A couple that maybe you've not heard of. There's one up here called iSwim, which is the root of all things trying to be purely functional. So we see Miranda under here, we see Haskell under here, we see ML under here, all derived from iSwim, and Fortran's at the top of BASIC, etc., etc. So very interesting that in this way of looking at programming languages, there are only a few roots where very interesting new ideas came along and then influenced a whole family tree underneath them. But really the family trees were derivative works of the interesting ideas that occurred in the roots, and there are not that many roots in the diagram. So why do we have 2,500 plus programming languages when the number of new ideas is actually quite small? Well, there are several reasons, I think, for this. And one of them is that vanity has a lot to play in which programming languages people use or which programming languages people choose to reinvent. And most of the interior nodes and the leaf nodes in the graph that I just showed are very, very small changes compared to their parent in that graph. Some small part of the syntax or the semantics or the meta system may have been changed simply to satisfy somebody's own personal preference. Or to scratch a personal itch that they have. Unfortunately, all too often, we also see people on committees designing programming languages, which is a bad idea to begin with, who all try to get their own pet feature included in the language standard. But this is evolutionary development of programming languages, and it's very typical of what has been happening since 1990. Now, before 1990, what was more typical was revolutionary change in programming language. When people still didn't have a language ingrained in them, they were still willing to experiment with new languages, and the education system outside of Argentina, I think there are a few places you can call an education system, really. It's a vocation system, are teaching the same handful of languages that they think industry will hire people for afterwards. But before 1990, we had Similar, which led to Smalltalk Self, JavaScript, etc. Lisp, which has a distinguished line of languages derived from it. And of course, iSwim, the obscure little language that had a very, very great deal to say about many things. But the innovation these days tends to be in domain-specific languages, and these are a little more than just scratching an itch. When people have a very tough problem to solve, and just thinking about that problem is difficult, they design interesting languages so that they can really think effectively about their problem. Given that we have many choices of programming language, some of them boring incremental development, some of them more revolutionary, how can we tell whether a programming language is fit for a particular domain or for solving a particular problem? And there have been many theories about this. One I like very much is to make an analogy between programming or computer science, as science is in quotation marks, and other sciences, in particular physics. And physicists are very, very clear. When you ask them what makes a good theory, they say that a theory has to have scope, economy, and elegance. And what they are talking about are their theories that describe natural phenomena in particular domains of the universe. And we as programmers really use languages as theories for how to describe the solutions that we want to implement for our particular problems. So if we look at scope, the physicists say that a theory must make intelligible a large number of phenomena. So the more you can grab with your single physical theory, the more successful that theory will be. Economy and elegance are kind of tied together to each other. Economy is we want to be able to write this theory in a very small equation, and elegance is we want to look at this theory and go, wow, that's beautiful. And we can substitute language for theory in here and come up with a pretty good idea of how we could measure programming languages' suitability for a certain problem or a certain domain. Now, the problem is that getting all of these three things right is very, very difficult. And if we concentrate too much on one, we sometimes compromise the other one. And in general purpose programming languages, we find very often that the scope is not quite where we want it to be. And this is what's driving domain-specific languages, because if the scope's not quite right, then the economy and the elegance go out of the window immediately, because we start building representations that we need inside an infrastructure that is unsuitable for those representations. And so the syntax of languages is important. The semantics of languages is important, but also underneath that is an often implicit model of how the values that you are working with are represented and behave. And an example I like very much of why this is important but often overlooked is the geometry program that was designed by Marvin Minsky and Gelernter the Elder, not the Linda guy, the one before him. And this was a program to make proofs in geometry. And it took 3 years for Gelernter to implement the program, and before the program actually ran, Minsky went back to his office and on a piece of paper simulated the execution of the geometry program using the representation that they had invented that was optimized for geometrical proofs. And even without running the program's design came up with a new proof for a Euclid theorem. So that shows that the representation is every bit as important as the syntax and the semantics that we usually associate with programming language. So every problem really that we look at can benefit from some kind of specificity. And a general purpose programming language really is a jack of all trades but a master of none. And so our economy of representation I think is proportional to what we call, anyway, the power of meaning in the things that you write down. And it's how much can you say with how little. And I'm going to take some examples of different powers of meaning. My two favorite extremes are in the United States. We have case law, which means that whenever you take somebody to court, a lot of very highly paid, overpaid lawyers sit around in a room looking at very dusty old volumes, trying to find a similar case, and if they found one that was judged a certain way, that's a precedent that says, aha, so your case must be the same. But if you print all of these out, it comes to 3 cubic miles of paper, and that's probably more than any one person can keep inside their head. Conversely, well, that applies to the United States, but something else that applies to the whole universe, to everybody, is electromagnetic phenomenon. So the thing that keeps me illuminated here, the thing that makes this microphone work, when you switch on the television, when you boil a kettle, etc., etc., 4 tiny equations are the entire program necessary for electromagnetism. We'll come back to that in a minute. To put the size of these things in perspective, a journal article, 2,000 lines of code, a textbook, Andres has some beautiful books out on the table, 400 pages, 20,000 lines of text or code. And we can go up to a small public library or a large private library. 10,000 books is about 200 million lines of code. Remember that number. 20,000 probably should be enough to have the meaning of most personal computer systems in our opinion. Now, the size is very important because as the size grows, the accessibility of a system diminishes. And the less accessible it is to a human reader, the less understandable it is. And if you can't understand something, you cannot effectively manipulate it. So, we have US case law, 3 cubic miles. I'm not sure how many millions of lines, billions, trillions of lines are in there. The Debian Unix system, well, partly because it collects many free software packages, is large, almost 300 million lines of code. Mac OS and Windows, in the same ballpark, 50 million lines of code. FreeBSD, very small, very light by comparison. And interestingly, some applications are larger than the FreeBSD operating system. OpenOffice, 10 million, and GTK, which is a toolkit that's used in quite a few open source, GIMP, for example, quite a few open source systems, is 2/3 of a million lines of code. Compare that to the thing that makes this microphone work, 4 lines of code. Okay, I can hear myself now. And Bill Gates said a few intelligent things in his career. One of them was that if you measure programming by lines of code, you might as well be weighing your prototype airplane, and as it gets heavier, you get happier. Now, 1 million lines of code these days apparently is considered small and efficient. And I get this again from the GTK release notes, where they claim to be small and efficient, and at the same time boast that they have almost tripled the size of their code base to 2/3 of a million lines of code. This to me is very curious, because I feel happy when I remove lines of code, not when I add lines of code. But my question really here is, it's a UI toolkit. It's 2/3 of a million lines of code. How can that possibly be? How much could they have saved if only they had used appropriate representations? Inside GTK, you find G-type, G-object, G-module, and lots of other G stuff, which has absolutely nothing to do with the problem they are trying to solve. And the problem here is that it's all layered above an immensely inappropriate language, which is C. And they are up against a rigidity of syntax, a rigidity of runtime, a rigidity of absolutely everything. And then the things they are putting on top, types, objects, modules, etc., are all very dynamic, very fluid things. So they're taking a static substrate to build dynamic content and seeing that it takes 2/3 of a million lines to get anywhere. So many thousands of lines have been wasted adding what should have just been in a dynamic substrate to begin with. So if you begin with a square punch, you are not going to have a good time making a round hole with it. And this kind of bloat generates several catastrophes. There's a vertical catastrophe, which is where the size of the system explodes as you go up because you are having to graft more and more mechanism on that really should have been given to you for free. And the horizontal catastrophe, which is the learning curve. As your system grows in millions of lines of code, the amount of effort to understand it goes up correspondingly. So the system, as it gets larger, becomes closed to understanding, to adaptation, and most importantly, to innovation. And I don't know if this has anything to do with the lack of innovation in programming languages since 1990, but maybe there is a relationship. Good representations, on the other hand, have a phenomenal power of meaning. Maxwell's equations, 4 tiny little equations that describe all of basically light, electricity, and magnetism. But what's interesting about Maxwell's equations is that they're not really Maxwell's equations. 2 of them come from Gauss, 1 comes from Faraday, the other from Ampere. And what Maxwell actually saw was a relationship between these theories that other people had missed. It's actually the same story with Einstein. His special theory of relativity was written way before he made it popular. But Maxwell's genius is that he understood that the form of the physical theory was as important as the function of the mathematics behind it. And he invented a new way of writing down the mathematics involved that unified and generalized the theories of the various people who came before him. And that meant a new clarity, compactness in the physical theory, and it meant many, many more people could understand it, could work with it, and could adapt it to real-life situations. So maybe if Maxwell had not written that down, we would not have microphones that work on radio today. So mathematics influences the way physicists and the way other people can think about very difficult domains. But language in general, not just mathematical language, but all kinds of linguistic structure influences how we manipulate models. And it can empower us or it can cripple us. And I need one volunteer, very, very quickly from the audience, who is a good orator, who passed elocution with at least 80%. Hand, please. Okay, please read the last 4 lines in a good speaking voice.
The really and the little toes, I don't know. And give us the, I don't know, that English. Or you see where the and the home rats out great.
Okay, that's about 3 times faster than I managed the first time I saw this thing. So it's nonsense, but it appears to make sense. Maybe not to somebody whose first language is Spanish, although the syntax is fairly similar to English. But to a native English speaker or to somebody who's fluent in English, even though it's nonsense, if you just glance at it, it looks like perfectly reasonable language. It makes sense even. You can kind of get a feeling of what's going on. Now, this is an interesting situation. Why does it kind of make sense? Well, linguists classify words into 2 groups. And the first group is what they call an open class of content words. And these are words that actually describe concrete things. Situations, people, actions, colors, sizes, times, etc. And so what I did, I stole an example from Wikipedia. And they have a wonderful sentence about how evil civil servants are. But if we substitute all of the content words, the things that tell us who it is, what they are doing, etc., and leave just the surrounding structure of the sentence, we can get an idea of what's going on, even though we have absolutely no idea who's doing it and what it really is that they are doing. But these are the words that describe the substance of our sentences, and they are called an open class because we routinely invent new ones. We can just invent a new noun anytime we like, or a new verb. I mean, the verb to Google was not in the dictionary 50 years ago, I believe. The other group of words that linguists have are called a closed class, non-content word, and these are the words that give structure to sentences. So now we've inverted the sentence, and what we have are all of the substance words have been placed there, but the non-content words that links them together have been turned into junk. And even though we know who it is and what they are doing and maybe why they are doing it, we are not quite sure who does it to whom, in what order, to what degree, etc. Because all of the structure that links that content together is missing. And this kind of word, it's the particles, the conjunctions, the order of words in certain languages, and in Japanese, for example, it's explicit little words, little particles that they put after the nouns and the verbs. This is called a closed class because we never invent new ones. When was the last time you thought, let's see, we need another particle to describe what I'm thinking about? We never do that. But that's a shame, because the content words tend to behave very similarly across all languages, both natural languages and mechanical languages, but the structure words behave very differently between languages. And we can see this because the structure of French and the structure of Spanish is very, very similar. And if you've learned French, then even though speaking Spanish is impossible, you can look at a piece of Spanish and understand what's going on, because a lot of the structure of what you're looking at is very similar to the French. Conversely, if you've learned French, then learning Japanese is still absolutely impossible. I have personal experience of the impossibility. Because the way you construct sentences in these different languages is very, very different. It requires a different mindset, a different way of modeling the ideas it is you are trying to express in that language. So the language itself, or rather the structure of the language itself, because even in Japanese, they have plurals, they have other ways of indicating indirect objects, etc. So very familiar grammatical things, but the way these are put together is so alien, it's very difficult. So learning different languages actually forces you to learn to think different ways of modeling what it is you are talking about. And even between French and English, if anybody knows a bilingual Canadian, someone from Quebec, it's very interesting to watch them talk in their family. They will zoom along in one language until they come halfway through a sentence to a concept that is slightly easier to express in the other language, and they will flip, maybe from English to French, in the middle of a sentence. Carry on until they come to the opposite situation, and they will immediately flip back to the other language. And they don't even realize they're doing it, simply because they're adapting the language they are using to the idea that they are trying to express. And this kind of reliance on the structure of our language and the way that the structure of the language modifies the way we use the content is learned very, very early as we are growing up. And there was a study that took young children and in play with these children, the researcher would use a nonce word, which is a nonsense word, a verb usually, and they would introduce it in the passive voice. And then they would notice that the children started using it in the active voice. They learned how the structure of the language was imposing rules on those nonsense words, and they could actually follow the rules even though the word was meaningless. And it worked both ways around. And the children learned to do this before they were 3 years old. So this goes very, very, very deep into the language programming inside our heads. And so we had a nonsense verb in the Lewis Carroll, outgrabe, which is obviously, to me, being an English speaker, the past participle of the verb to outgribe, of which we have the progressive outgribing, etc., etc. And we could invent any number of sentences in which this meaningless verb appears to make perfect sense. So his words conform to our expectations, which are driven by the patterns and the transformations that those patterns imply in the language that we use. And it's the non-content words, not the ones that we routinely invent, but the ones we never, never reinvent, that actually drive the manipulations we can do on the content. So we can only conclude that the structural form in language is what drives and restricts in both directions the behavior of the content we are trying to express in those languages. It's interesting in the phonetic, in the natural language domain, it works phonetically too. And if anyone's interested, afterwards I can play you a piece of music which is obviously in French, except that I speak French and it's not French. It's nonsense, but phonetically it sounds French. So although these different structural systems have very different rules and manipulate their content in very different ways, it is possible, and because we can translate between natural languages, it's been clear for a long time, it is possible to have equivalent representations in them. And if we go back to mathematics, around just after the turn of the 20th century, there were two theories proposed within a few years of each other. Heisenberg says the first thing, Schrödinger says the second thing, and which of them was actually right? Because the whole universe depends on which of these two equations was correct. And anyone who's studied physics may say, well, clearly the second one is right. And anyone who's studied the mathematics behind the theory of quantum mechanics will say, well, clearly the first one is correct. The first one is expressed in terms of matrices. The second one is expressed in terms of partial differentials on wavefronts. So the second is perfectly natural for a physicist. The first one perfectly natural for a mathematician. But the semantics underlying those representations are identical, and they will make identical predictions about physical systems. However, give the first one to a physicist and he'll be lost. Give the second one to a mathematician and they'll be scratching their heads, trying to visualize what's going on in 3D. So the domain-specific representation in mathematics can be a tremendous enabler for a particular community. But it also encourages them to think in certain ways. In the first way, it's evolution of matrix equations. In the second way, it's thinking about how things propagate through space. And so I said in the abstract that Dijkstra made a comment about the tools we use in programming, and the programming tools we use are exactly the same. Our choice of tools, in particular our choice of programming language, has exactly this effect on the way we think. So the character in a programming language, like the character in a natural language, is all down to the structural content. So the nouns and the verbs are completely irrelevant. It is the particles, which in programming languages are the restricted keywords, they are the punctuation symbols, the semicolons, the parentheses, the commas, etc. And these are a closed class. There are few programming languages where you can routinely invent new punctuation symbols and start using them. So a suitable grammatic structure can facilitate programming greatly. And I think anyone who, you're all small talkers, so you know that the object-oriented paradigm is a very powerful facilitator for certain kinds of simulation and modeling. But I want to go one stage further than that. An extensible grammatical structure can generalize a language in a way that has never been done by a popular programming, a general-purpose programming language. And so here's an example. Of a programming language, and this could be any of a half a dozen different programming languages. You can't even tell. You can tell what class it belongs to, though. And on the left is the structure, and on the right is the actual content that tells you what it's doing. You can look at the left-hand side and get a pretty good idea of how the program will behave when it runs. You can look on the right side, which is telling you exactly the domain that the program is working in, and you are completely lost, except that you could maybe infer that RE means real and IM means imaginary. That's about as far as you will get. So, the domain-specific languages, which is where most of this innovation is happening today, are actually very common in use. And most of the people in this room will have used one of these languages on the slide, I am sure, on a daily basis. They fall into, they can be divided along two axes. And some domain-specific languages are for experts to be able to invent solutions in a very restricted domain, whilst others are for non-experts and they open an otherwise closed domain to non-expert use. Along the other axis, we have domain-specific languages that are standalone and meant for describing applications within themselves, and others that extend more general purpose languages in which they are embedded. And that's really the class that I am most interested in today. Here are some examples. Mathematica is designed to look just like mathematics to a mathematician, with a few extra decorations for plotting. APL is designed to look like meta-mathematics for meta-mathematicians. And if I can make my little pointing thing work. So at the bottom line here, for example, says distribute the function plus across the vector n. So it adds up all of these numbers. So 3 characters do what would maybe take 15 in most programming languages. So this is an incredible economy of representation, but when you start getting excited by it and doing more interesting projects, you come up against the write-only program syndrome. Now, anyone done APL, please raise your hand. We have 1, 2 takers. You are very, very brave because you're not going to tell us what these programs do. 3, 2, 1. Okay, yes? APL, yes, I know.
I can't remember.
You can't remember, okay. That's right. I think these programs are on page 19 of the manual, by which time most people have switched off. So yes, no chocolates or cookies for anyone today, I'm afraid. The first one is sort, expressed in APL. The second one is a prime number generator. The other problem with these kinds of languages is often that we have Unicode these days, but back in the days that the languages were invented, you couldn't even program in these languages unless you went out and bought a very expensive keyboard that had weird symbols all over it. But this kind of domain specificity and this kind of representation and abstraction can be made a little more palatable to the programming languages we use these days and still be of very great effect. So I had fun a few years ago writing a set of C++ macros that would generate machine code on the fly. Effectively, it was an assembler that ran when your C program ran, that given something that looked like an instruction would assemble the binary, the bits that were necessary in memory to do it. So here we see at the top the 10 basic instruction formats listed in the PowerPC manual. At the bottom are some PowerPC instructions written in terms of those formats. So already we have a domain-specific language here, which is the domain-specific language of the internal structure of instructions, and another domain-specific language here that is built on top of it, which is the assembly language of the PowerPC expressed in terms of the domain-specific language underneath, the basic instructions. Now Intel, of course, always having to outdo Motorola, have at least this many basic instruction formats. It's really a nightmare. But you can do the same exercise with that. You can write down the format of a 386 instruction, and then some 386 opcodes in terms of those underlying formats. And then you can do interesting things like writing C programs that include those instructions, the macros, that then generate machine code on the fly. Very useful for certain kinds of runtime optimization. So here we have, within a single system, several different levels of abstraction, each of which is expressed in the language of the system, but each of which allows you to think in a way that is particularly suited to that level of abstraction within the system. And we can go a certain way within the syntax that's imposed by the language, but at a certain point, the noise due to the impedance mismatch between what we are thinking and the language we are given to express it in starts to accumulate. And so we can improve this, at least at the top level, by some pre-processing. And so I wrote a little preprocessor that would take something that looks just like assembly language to an assembler and would turn it into the macros that we saw a few slides before. Now, being a Smalltalk conference, I would have felt very guilty if I didn't talk about Smalltalk on a slide. So here's another example. This is a Smalltalk program that parses Smalltalk programs, and it's written in Smalltalk. And it almost looks like a grammar. You can see there are ways of matching character classes to create unary, binary, and keyword messages. There are message sends for repetition, 0 or more, 1 or more, etc., etc., and a little bit of stuff in square brackets, which is the semantic actions to do when you match something. Now, Smalltalk has a particularly simple and therefore general syntax, which means that you can do a lot with it. And this really doesn't look bad to a parser writer, but you study it, it could clearly be helped by a little bit of pre-processing. And here is what it would look like if you were to write it as a real grammar, keeping the semantic actions with each of the rules. And I thought it was an interesting exercise to take this and subtract it from the previous slide to see what was left over. And this is what's left over. This is the noise that is in your program simply because of the syntax and to some extent the semantics that Smalltalk imposes upon you. This is the stuff that you wish you really hadn't had to write in your program. So what can we do to get rid of this clutter? This is a trivial example, but when working in much more complex domains, the clutter of the noise can be a 10-to-1 ratio or even worse with the actual content you're trying to describe. And dealing with the clutter stops you thinking effectively or maybe even at all in your domain. Well, there are some DSLs specifically to help us with this kind of problem. Everyone's seen regular expressions. The language theorists all understand context-free grammars, which is a large class of both natural and artificial languages that includes pretty much every programming language that we use. And so these domain-specific languages can help us to write those preprocessors for our embedded languages and do a source-to-source transformation so we can write things the way we want to think them and have the machine translate them into something it can execute automatically for us. So we will match a pattern in the more abstract domain that we are thinking in and substitute a different representation that's less abstract that the machine or the compiler or the interpreter or whatever can deal with directly. We could write this as regular expressions. They are powerful enough in most cases, but they are very cumbersome and they do have limitations that we come across sooner or later. We could write a parser using a real parser generator tool, but this is difficult for non-experts. Non-experts generally, when faced with a parsing problem, write a recursive descent parser. And a recursive descent parser is a very simple approach of a normal program that just marches through the definition you are trying to match, looking for each piece in turn, and either returning an error if you don't find it, or constructing some piece of tree or other structure to represent the content that you did find. Now, this can be automated using a domain-specific language, and if you want to investigate that, the parsing expression grammar, I think, is the simplest one for non-language theorists to use, because it looks a little like a grammar, but really it's a description of a parser, and it's a very compact way of describing exactly that recursive descent parsing that was written out explicitly in the slide before. What it adds to regular expressions, which it's very closely related to, are a way to name rules so that you can call subrules in a grammar, and it replaces parallel search through the grammar with an ordered choice, which is much more the way we program. Is it one of these? No. Well, is it one of these? No. Is it one of these? Yes. Well, we don't care what else it might be. And the actual syntax of pegs are very, very similar to regular expressions. And so this is our recursive descent example, again, written out as a peg. And now it looks very much like a grammar, except that it is trivial to convert this into the program, the 15-line program we saw a few slides earlier. The grammar for parsing expressions fits on one page. These slides are very big, so it looks like two. It's really one page. And you can translate that by hand very simply because it describes a recursive descent parser. So for each of the rules in there, there's just a few little lines that you need to generate. Do this once by hand. You only need to do it once. It'll take an afternoon, after which you can feed it through itself, and things become very, very much faster. And now extending that with whatever you need in your own structural transformation description language is very easy because you now have the tool for writing matchers and generators for your source-to-source transformations. Now, what's interesting is that when you combine this technique with a dynamic programming language, one like Smalltalk or JavaScript, or the ultimate is Lisp-like languages where programs and data are exactly the same thing because the manipulations become incredibly powerful. And so anyone who's got gray hair like me will remember from compiler class the old T diagrams that they used to write, which is source language on the left, target language on the right, and then at the bottom it's the language in which your translator is written. And you can play Lego with these to create ways of implementing systems. But in a dynamic language, when you have the source-to-source transformation embedded in the language, your T diagram ends up looking like this. And this is a very, very powerful situation to be in because it means you have complete control over the way you are expressing your programs. So we have two ways of solving a typical situation, which is we are given a specification in one language and we're given a different programming language to implement it in. We can sit down and hand translate the spec into our programming language, but it's always a little iffy whether we did that correctly. Now we have a second option. We can take our programming system and teach it to understand the spec. We can take the system to the spec and write an embedded source-to-source translator that will do the translation for us. Now, the advantage of this is that it finds bugs in the spec, which might be useful to the original designers of the spec, but secondly, any mistakes in that recognition process tend to be catastrophic. So if there is a little bug hiding there, it will not work. If it's perfectly correct, it will work. This is much better than worrying whether there's one little line wrong in your translation in the other direction. I will do a quick example for you, and I had occasion to need to use my CPP macros that I wrote for the assembly in a Lisp-like environment, and I thought, well, I could spend 2 days translating these and going crazy, or I could spend 30 minutes writing a little bit of helper. And so this is the helper that I wrote. It is a parsing expression grammar that describes what a C++, not a C++, a C preprocessor macro looks like. The right-hand sides, which are a little bit jumbled up because the terminal is not wide enough, the right-hand sides generate equivalent S expressions. So I teach my system how to understand the input that I have been given, and then I just feed it those macros that I showed you on the slide before. And when I run this, you see, when I run this, it conveniently spits out for me exactly the same content, but now in the form that my system can use immediately. I could either save this to a file, or I could just feed it directly to the evaluator, and it would instantiate all of the functions that I need to use those CPP macros inside my Lisp-like system. So how far can we take this idea of making source-to-source transformations illuminate our thought processes? Well, again, those with gray hairs similar to mine in the room will remember green and white stripy 132-column paper, punched cards, Fortran manuals, cheap Mexican beer, but most importantly, wall calendars. And the calendar, in all of the computer rooms that I was in this phase of my career, had a Snoopy calendar, and it was always the year 1969. I think some of us old-timers just lament the passing of the 60s. Certainly lament the glory days before Unix took over. So this is ASCII art for dinosaurs like me, and we can have a lot of fun with the teletype, inventing new animals. But is this really serious? Well, Yes, it is, because back before the days of PDFs, to communicate an idea usually involved drawing a picture of it. And this is taken from the Boehm Diemers-Weiser garbage collector describing the layout of structures in memory. And looking at this is worth 1,000 words of description how the program actually works. Now, it turns out that ASCII art, being a kind of formal system, well, certainly when you start drawing data structures with it, it has a grammar all of its own. And we can express it in a few lines of code. And if I feed this to my system, I can now write a program that looks like this. And I've cut and pasted this from the RFC that describes what a TCP packet looks like. And it's just a picture of a packet header, but now to my system, because I've brought the system to the spec, it's a piece of source code. And I can feed this through the system, and it generates the data structure for me, and all of the functions needed to manipulate that data structure. And this is a cute little stack. It's 100 lines of code in total, and it will serve up HTTP for you. So source-to-source is possible to varying degrees depending on your language. You can even do it offline. So there's the CPP macro thing. You can invent languages, very limited languages, and do funky transformations there. Online, in our dynamic languages, it's very much more powerful, and it's a technique that everyone in this room should take seriously, especially when tackling a problem that has very specific ways of thinking and representing the programs. So pegs are very easy, much easier than things like Bison and Yak, but they do have limitations. And if you want to play with a real grammar, one that is just as powerful as you can get without going off into hyperspace, then the one I would recommend you look at is called an early parser. And these ones are beloved of the natural language people because they can deal with ambiguity. You can feed it an English sentence and it will tell you all 79 ways that that English sentence could be interpreted. But they are extremely simple, and they deal with the whole context-free class of languages, which includes a minuscule part of it are the programming languages that we use. And it works with grammars that would kill most parser generators stone dead. If we feed left recursion to a peg, it stops dead. If we feed right recursion to a Yak or a Bison generator, we either get a string of error messages we can't understand, or when we run it, it stops dead. With an early parser, if you can write the BNF spec, the language spec for your language, your parser will parse it. It's very simple. This again is taken from Wikipedia, and it's easy to translate. It takes 30 minutes to translate that into a programming language, and it works extremely well. I will show you an example of that maybe, although I'm running a little low on time. They work very similar to regular expressions. The good way of implementing regular expressions is to turn them into a finite state machine and then concentrate on the edges. We build a list of edges out of where we are. For epsilon transitions, that is an immediate edge that doesn't depend on the input, we append that to our current list. For an edge that depends on the input, we check if we have the input and append it to the next list of things we look at. When this list becomes empty, we swap the two lists. We now have an empty list over here, and we have our next stage here. We consume our input token, rinse and repeat. And this is an incredibly efficient way of implementing regular expressions. An early parser works exactly the same way, except that it doesn't have just two lists. It keeps the list for every single space between tokens. And at the end, you can read out of the chart, which is just this collection of lists, you can read out all the possible derivations of your program. So you need to be able to disambiguate this, but that's usually fairly simple. Just take the leftmost derivation for a programming language, and that's typically the parse tree that you want. 45. I'll go very quickly with this. Let me see. Hello? Okay, so here I just have two grammars. I fed it an expression. One contains left recursive rules to do the operators and the precedence. The other contains right recursive rules. The early parser deals with them both, with no special things at all. It's a 40-line program. A peg would have died on the first case, and an LR generator like Yak or Bison would have died on the second case. Very easy to understand and implement. Go look at them if you're interested. Whoops, wrong way. This way. So, just a little aside, the natural language people love this because natural language is so ambiguous. We have sentences like, time flies like an arrow, or I saw a man on the hill with a telescope. Well, who had the telescope? We don't know if it's me or the man on the hill. According to the Oxford English Dictionary, the 500 most used words in English each have, on average, 23 meanings. So, quite a parsing task. So pattern matching plus output generation in your programming system is structural transformation. The structure dictates how you think about something. If the structure you are given to program in is not the one you want to think in, build yourself a translator within your system. The more deeply you do this, the more powerful it gets, until it starts to smell a little bit like mathematics itself. And we can make a statement about implication and then make a non-implication about implications, which is almost showing you that we have a meta-implication operator telling you that the left-hand side does not imply the right-hand side. It's not quite meta-mathematics, but it's starting to smell like it. And systems that can deal with their own representations and reason about them become very much more within your grasp in a dynamic language if you embrace the source-to-source transformation of syntax and semantics, if you can go there. I'll show you this because it's a Smalltalk conference. So what I thought I would do is teach my little system here about the syntax of Smalltalk. And so you can see we have, let's see, unary messages, binary messages, keywords, blocks, primary expressions, keyword send expressions, assignments, everything you would normally find in a Smalltalk program. So I fed this into my system that has one of these little built-in source-to-source translators, gave it a little bit of context at the beginning, 40 lines or so of code, and now I can start writing. Well, I start off, of course, describing my object hierarchy, and now I can start writing programs in Smalltalk. This is not a Smalltalk implementation, but it's now an implementation of another language that understands Smalltalk syntax and Smalltalk semantics. And I will run that for you just to prove that it's not vaporware. It will think a little bit because it's constructing everything from scratch. There's my class hierarchy, there's the source code to a method, and there's the Smalltalk program actually running. It's doing a fast Fourier transform. So if I was asked to think in Smalltalk but given Lisp to write in, this would be my approach to doing it. So we have a way now of modeling syntactic transformation in language. Doing the semantic transformation in language is almost as easy. And it helps a lot to think of languages not so much in terms of what the programming manual says, but more in terms of what you are trying to do with the language, like nouns and verbs and adjectives and adverbs. And if we recast our programming language thoughts in these terms, it starts to become apparent how we can manipulate the semantics of languages. Now, of course, the father of all self-describing languages was Lisp, and it describes its own semantic using eval and apply. Which is a little bit restricted because eval and apply have certain domains built into them and they cannot escape from these built-in assumptions. But with a little bit of generalization, which is suggested by the principle of composition, which tells us given the meaning of individual elements within our program, there is a meaning function that relates that to the meaning of the overall expression. So given some structure in my program with elements, the meaning of that is given by a meaning function applied to the meanings of each sub-element in turn. This is a principle that's much more wide than programming languages. In the whole of semiotics and semantic research, this is a very strong principle, and we can apply that to programming languages too. And we can ask, how do we generalize the semantics of our language so that we can treat it as malleably as we can the syntax? And today I don't have time for that. Maybe this evening, if I have 10 minutes more, I will go into that. Binding time. And time is important as well. So this is very often neglected in programming language descriptions. The one notable exception I know is the C standard, which tells you 12 different stages between the source code and the executable code and what actual transformations are happening in the representation at each of those stages. But that can be modeled explicitly in this kind of system as well to make a very powerful semantic manipulation as well as the syntactic manipulation. So I'm almost out of time. I will do some summary and conclusions, beginning with a recap. So the content words, which are the ones that the procedure names, the variable names, the things that we invent every day, work very similarly. So it doesn't matter if you're writing in Fortran or in Smalltalk. Generally, the identifiers are identifiers. The non-content words, which is both explicit, punctuation, reserved words, keywords, but also word order or in natural language conjugation, is what gives a language its character, what's helps us to think certain thoughts in that language. We almost never invent new ones, and there are few programming languages that encourage us to invent new ones, which is a great shame because that is where the power of our thinking really lies. Suitable grammatical structure makes it easy to write suitable programs, but an extensible one makes it easy to write almost any program. And this is related very much to participatory design. In the physical manufacturing industries now, we are seeing a rise with desktop manufacturing, the laser cutters, the 3D printers, etc., of designs of physical artifacts where the end user is sat down with the designer himself and they participate to make sure that that product will be perfect for the application the end user has in mind. And our programming languages should really follow the same model. However, it's impractical that a designer of a programming language can sit down with 1 million users. However, that designer can think ahead of time about how to build their system to encourage aftermarket modification of the syntax, of the semantics, and maybe even of the representations underneath by the end user and for the end user. And I hope today I've demonstrated that it's not hard to do that, at least on the syntactic level with your programs, and the benefits can be quite significant. It's curious, we're going all the way back now to 1958, where John McCarthy proposed a program that was never written called the Advice Taker, which had many of these aspects of self-reference and self-modification inside the system. Now, if we go to a completely different domain, in 1969, a conceptual artist from New York, Mel Bochner, took 10 years out, or started on a 10-year journey where he thought about what art actually means. And what does it mean to create a design on a canvas, and what are we communicating, and how are we communicating with the audience that look at that? And this is one catalog card that he scribbled on, where he relates the act of thinking, the necessary support for us to think about things, and then the effect that the physical representation has on the presentation of those thoughts from the artist to the audience. And he came up with this big long thing, which he paraphrased by painting on a wall, that language is not transparent and that no thought exists without a sustaining support. It's impossible to think of something without actually having an underlying substrate for it. The language affects how we can communicate what we are thinking about, but also the support underneath affects the range of things that we can effectively think about. So from language, it's syntax, semantics into pragmatics, and the sustaining support is representation up into pragmatics. And if you ever need a convincing argument why programming is not science but is art, then please feel free to reuse this argument. I have some suggestions for further reading on these topics, and please come see me afterwards and I will explain why I think these are good. Henry Baker was the first I think the first to embed a general parsing technique into a dynamic language. Of course, John McCarthy, if you haven't read this book, you need to go and read this book. If you haven't read this book, it's full of great ideas of semantics and little programming mechanisms that you can attach to the syntax that you might use in your source-to-source transformations. And this is the obscure one that really anyone interested in functional programming absolutely has to read, and it's the Peter Landin paper. This language ISWIM was never implemented, but it has a huge influence on the functional programming languages that we have seen since. So what was all this stuff about mice and mousetraps? Well, Thomas Edison, who was 23rd in line, I think, to the patent office for the light bulb, said once that if you build a better mousetrap, the world will beat a path to your door. Well, if we consider that the solutions to our problems are the mice, and our mousetraps are the languages that we use, if we follow his advice, all we'll be doing is catching more of the same mice, or maybe less time for the one mouse that we are trying to catch. But we're still not thinking any better because our mice are the same old mice. If we insist on better solutions, then the better languages, if our system lets us play with that part of the representation, will follow those better solutions. So let's try and invent better mice and see what the trap might look like to trap them. So apologies to anybody who might have come here expecting me to talk about this particular mouse, but I will very, very quickly offer up this as a consolation surprise. Let's go back to the nonsense. and consider this. I had no idea until I started looking at all of this linguistic stuff. Brill means to boil. Brillig is a time of day, hence the sundial at the top. It's 4 o'clock in the afternoon, and of course Argentinians all know that at 4 o'clock you need to boil up a snack. Slithy toads. Slimy is a slimy, lithe creature. A tove is one of these badger-like things, and they are gyring, which you can see is spinning around. Gimble is to dig a hole, which they do by gyring. The wabe is this grassy slope that they are digging holes in. The mimsy is flimsy and miserable, and the borogoves, which are these birdies you can see are pretty flimsy and miserable at the same time. The mome wrath, they're these little piggy creatures in the back, and they are outgrabing. And outgrabing is something like a bellow and a whistle with a sneeze built into the middle of it. And so if anybody wants to attempt that later, maybe we need some beer first. My consolation prize to the mouse people in the room is that, where's it gone? Gyring, gimbal in the waves, outgrabe. Grabe comes from grike, which comes from shrike, which we derive shriek, which means squeak. How's that? Whoa. So you probably have a very fast dynamic language, and if it's not Gemstone or some other Smalltalk, then it's probably JavaScript, because it's in every browser that you own. You can build a PEG or an early parser. It'll take you 100 lines. It'll take you 1 afternoon, if that. And after that, it's your bootstrap into an amazing world of source-to-source transformation that will empower your thought. So please go home and build some better mouse thoughts and the traps in which to snare them. Thank you very much. Okay. Okay, so, yeah, sure.
Thank
For example, the TCP/IP example that you showed,
Yeah.
how can you use that?
Okay, so I am very interested and trying at the moment to build descriptions that are like lingua francas, intermediate languages between high-level representations. So I have made some attempts to make these transformations run in reverse. So you describe the transformation in one direction, and the system infers how to translate in the opposite direction. Now, if you can pull that one off, you can take any source language, translate it into an abstract form, and then untranslate it back into any other programming language. Now, the semantic problems involved there are huge, but that's what makes it an interesting problem. And any number of PhDs could come out of this. But being able to share that level of semantic information and representational information is an extremely powerful thing, and I hope we can crack that problem. And I will be around for the whole conference, so if anybody wants to ask me questions offline, I would be very happy to sit down and talk about any of these ideas.